it's me again. This is another one of those problems where they've given us a function and they've just left a little information out, and they're asking us to make this a continuous function. Here, there is some mystery number right there that we need to figure out in order to make this function continuous everywhere for all real numbers. And so as we've been doing with the others, I'm just going to make each one a different color. So our top rule is a little bit more complicated than some of the others. And just by looking at that, I notice like, ooh, if x equals 5, that's going to be an issue because it would make the denominator 0. Well, good news. X doesn't equal 5. For the bottom rule, that's a linear function. It's 2x plus some number. And so that definitely doesn't have any issues. And so our only potential problem is that switchover point. We need to make sure that the limit from the left, as x approaches 5 from the left, is the same as the limit as x approaches 5 from the right. So, among other things, there are a couple other things we need to check, but we're starting there. Remember the definition of continuity. First part is that your roads have to meet. So our two-sided limit has to exist, which means the limit from the left is the same as the limit from the right. And once again, I'm focusing on a 5 because that's the only spot where anything could go wrong. That's where we're switching from the pink to the red. So, if we're approaching 5 from the left, we're looking at x's that are slightly less than 5 and getting closer and closer and closer. So that's going to be a job for the top rule. And this is going to take a little bit more effort than some of the other examples we've seen for continuity, but it uses the skill that we saw earlier in the unit. So here I have still included the fact that I'm approaching from the left, but it really doesn't affect my work. Approaching from the left is how I chose the red rule. And so in terms of finding this limit, at this point it's just a rationalizing problem. So that's something we've done before. So since I see 2 minus a square root, I'm going to do 2 plus that square root on top and bottom. That's the only thing that should change. Notice that it's still an x minus 1. The only change that happens with rationalizing is that sign that connects the radical term to the other term. And so when we start simplifying that or just putting those pieces together, again, from the left doesn't matter a whole lot. The numerator was where we had the issues, right? The numerator had the square root. So I want to fix that. But the reason we chose those different signs, one subtraction and then we made the other addition, is to make this pattern work. 2 times 2, pretty sure that that's 4. A negative square root times a positive square root becomes a negative non-square root. And I multiply that pair. The other pairs would be positive 2 times square root of blah, 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 and then negative 2 times square root of blah, blah, blah. So the pattern allows me just to skip over those. That's the whole reason that we changed the sign from subtraction to addition. So now my numerator looks nicer. It doesn't have a square root. And the denominator, I am not going to take the time to multiply all that craziness out, because that's going to end up looking a lot worse and will kind of defeat the purpose. So I'm just going to leave that alone, leave it factored, because my hope is that this x minus 5 is going to find somebody to cancel with in the numerator. So keeping the limit in front because I still have x's, my denominator has all of this craziness. X minus 5, 2 plus square root of x minus 1. And my numerator is 4 minus x, and then this minus that is now a plus 1. So really I have a 4 plus 1, which is 5, and then minus x. Sometimes students will see those and they'll be like, oh, those are the same, they must cancel. But if we think about it for a second, they're not really the same. Think about, so I'm just going to make up a random number at 13, just to kind of prove a point off to the side. So just totally random choice, 13. 5 minus 13 over 13 minus 5. Just focusing on that pair to show why they're not the same. 5 minus 13 is negative 8. But if I subtract in the opposite order, 13 minus 5 is positive 8. So they don't cancel, but they do reduce to a negative 1. So sometimes students will just say, oh, those are practically the same, just the signs are backwards. So they just say they sort of cancel, but to negative 1. What some other students would do is say, well, if this is 5 minus x, I'm going to factor out a negative 1, and then I have a negative 5 plus x. And then this factor and this factor are exactly the same, written in the opposite order, but they both have a negative 5 and a positive x. But either way, we should have gotten to the point that yes, that x minus 5 did cancel, but it left us with a negative 1. And then 2 plus square root of x minus 1. We still have x's in our work, so we still have the limit notation in front. But now that something has canceled, we're ready to take care of the rest. So my next step, negative 1 over 2 plus, direct substitution, 5 minus 1. Okay. And because I don't have any x's left, that's why I don't have any limit notation in front anymore. So that's the hard part, because what we just figured out through a fair amount of work, clearly, we just found the limit as x approaches 5 from the left. We just figured this out, found that it equals this number, which if we simplify, because we'll have to do some more stuff later, it's a negative 1/4. Okay? But that limit was tougher to do than the other one we need to do. So I'm going to do a little scribbly there, because we just did all the work approaching from the left, but we also need to do the work approaching from the right. Fortunately, that's much easier because we're working with a much simpler function when x is bigger than 5. So the limit as x approaches 5 from the right of this function is going to use the blue rule, limit as x approaches 5 from the right, or whatever, 2x plus b. Okay, because now x is a tiny bit bigger than 5. And so this is just direct substitution. Instead of letting x approach 5, let's just plug in 5 for x. So this is going to give me 2 times 5, right? Only the x gets replaced. The b is still a b. And so my limit from the right took a lot less work, and we got 10 plus b. So let me go back and recap what we've done so far and why the hard part is over. The limit as x approached 5 from the left, we used the pink rule. We had to do a bunch of work with rationalizing, and we found this. Just to avoid confusion later, I'm going to erase my little example there. The limit from the left is negative 1/4. The limit as x approaches 5 from the right is 10 plus something. But in order to be continuous, we need those two things to be equal. And so that's really our only remaining job. again, we need the limit as x approaches 5 from the left to be the same as the limit as x approaches 5 from the right. And we've already done the work to find each of those. The limit from the left, after a bunch of work, we got -1/4. The limit from the right, after a little bit of work, we got 10 plus b. And those need to match. The roads need to go to the same place. And so then, we're in good shape. -1/4 minus 10 is that missing b value. So what's that, -41/4 if you simplify? All that we've officially done here, like we have an answer. All that we've officially done is we've made sure that the first part of the definition of continuity is met. We have made sure that the two-sided limit exists because the limit from the left matches the limit from the right. That would happen if we put a -41/4 in that spot. Officially, the definition for continuity has a couple more pieces, but if I didn't make sure these pieces were taken care of, then it would be a terrible question. So I'll do this just off to the side over here. Let me make that slightly easier to see. The second thing, like we know the value of b, so really we're finished here. But the second thing is that f of 5 needs to be defined, which means that if x is exactly 5, I need to be able to plug that in somewhere. And the good news is I can. I know it's a little bit hard to see, but the blue rule was for x greater than or equal to 5. So cool. And then finally, the limit as x approaches 5 from both sides, that needs to match the function value. The limit as x approached 5 from the left was -1/4. And then we did some work to make sure that the limit from the right, 10 plus b, was also -1/4. And f of 5 uses that blue rule. So this requirement was kind of automatically met through the other work that we had done, because my limit from the left and from the right is -1/4. F of 5, the blue rule, if you want to get real fancy with it, it would be 2 times 5 minus or plus -41/4. And then that's 10 minus 10 1/4, which is indeed -1/4. But that kind of just automatically happened through the direct substitution that we did earlier. So what I've done on the left side of the screen, on the white background, is really all that was necessary here. Once we found the value of b, then that was it. That's all I had asked for. That's the only thing that you really had control over to make this thing continuous. But just as a reminder, the other two parts of the definition are here. The bridge exists and the bridge is in the right place. So you'll see some examples of this in your homework, and hopefully these videos are going to help you work through some of those. And of course, office hours and asking questions and all that. So bye guys.